Okay, let's get started. So today we're moving on through Chapter 10. We're adding some additional modifications to the Rankine cycle. So we're going to look at the second law analysis and then also cogeneration. And if we now think about a vapor cycle and the realm under which it has positive operation, and a gas turbine cycle and the realm under which it has positive operation, we can combine the two to get kind of the best of both worlds and increase the efficiency overall. So that's what's coming for you today, later in this exciting edition of thermodynamics. Okay, so the ideal Rankine cycle is internally reversible. It's not totally reversible. So internally reversible means that we can return the cycle to its original state without the cycle being affected, but the surroundings have an effect upon them because we're transferring heat. We can never do that in a reversible manner. So even though we may approximate our turbine and our pump as isentropic, meaning they would be reversible, our entire cycle is not. So the heat transfer prevents it from being a totally reversible cycle, which means that we are destroying exergy in the process, which also means that we're generating entropy. So when we look at the second law analysis for the Rankine cycle, and we want to determine the exergy destruction for it, we would follow the equations given here. So this is the rate of exergy destruction is equal to the sum of the mass flow rates times the entropy of all of the outlets minus the entropy of the inlets. And then we use the Q outs and then Q ins in that way too. I think this is supposed to be a negative here actually. So we're adding the entropy coming in and we're subtracting the entropy leaving the system. So the exergy associated with the whole cycle itself depends on just the inlet or the initial and the final state, which is the same state, which means that we're only considering the exergy destruction due to the external implications of the cycle. So because our fluid returns to its original state, its entropy does not change. It changes throughout the cycle, but the overall view of the cycle is that it's the same. So we're just looking at the heat transfer with the environment when we consider the whole system or the whole cycle together to determine the exergy destruction. And at any given point throughout the system, if we're looking at these steady flow engineering devices, we can calculate the exergy of their fluid streams using the equation given. So it's three different things we're looking at. The first is the exergy destruction of a steady flow device. This is the exergy destruction of a cycle, and then the exergy itself of the fluid at any given point. Okay, so make sure you understand the distinction between those three different equations. So the exergy destruction for the simple ideal Rankine cycle is fairly easy to analyze and calculate because from state 1 to 2, if we're assuming it's the ideal Rankine cycle, our entropy does not change, which means that we have not destroyed any exergy, nor have we generated any entropy. So for our pump and our turbine, our exergy destruction is 0 because they're isentropic. Again, this is only for the ideal Rankine cycle. The exergy destruction from state 2 to 3 is going to be equal to T naught, which is our what? Dead state temperature, and that should be given in the problem, or if it's not given, what do we assume? Yeah, 25 C or just 300 Kelvin. Okay, so just room temperature. Then we need to know the entropy at state 3, the entropy at state 2, and then we need to know how much heat is coming into our system between state 2 and 3 into this boiler, and we also need to know the temperature of the source. So within our boiler, we can calculate our heat input, but if the temperature of that heat input is not given, it's difficult to calculate the exergy destruction. So that information needs to be known. The second part of this, if we're looking at our condenser where we have a Q out, we can calculate the exergy destruction in the condenser due to that heat transfer with the environment. And again, T naught is the temperature of the dead state, where T sink is the temperature to which we are depositing that heat, which in many cases is the same as the temperature of the dead state because we're just getting rid of the heat to the environment. Now we can look at the second law efficiency in terms of the exergy recovered over the exergy expended. There's also an alternate way of looking at the second law efficiency, and that's the thermal efficiency of the actual cycle divided by the thermal efficiency of the reversible cycle. But for the second law efficiency, if we're looking at exergy recovered, that always comes when we have some work output. So the exergy recovered in a system is the amount of energy that we're actually taking for a useful purpose. So we're recovering some of that available energy and actually using it. So work output is generally the only term that you'll find for an exergy recovered. Exergy expended is always going to come in the form of any heat transfer or work into the system that is required. So there's energy coming into the system due to heat, and then there's energy coming into the system due to the work that we're putting into the pump. So that is the exergy that is expended in this process, meaning the exergy our system is gaining, and the exergy recovered is the amount of energy we can actually take and put towards a useful purpose. We could also look at the second law efficiency in terms of the exergy destroyed. And in this case, for the ideal Rankine cycle, we just have the exergy from 2 to 3 and 4 to 1, because we're not destroying any exergy in our isentropic turbine. How would this be different if instead of having the ideal Rankine cycle, we had a turbine and a pump that had some isentropic efficiency associated with them? How would we then calculate the exergy destruction for states 1 to 2 and 3 to 4? So if they're not isentropic, they have some isentropic efficiency, meaning they're not reversible. How do we do that?
Would it be the dead state times the change in entropy?
Mm-hmm. And depending on whether or not we can assume our device is adiabatic. Okay, so we may have some heat transfer. If that information is given to us in the problem, then we use it. If it's not given, we have to make other assumptions. But yeah, we need to know the entropy difference between state 1 and 2. So in order to do that, we oftentimes use the isentropic assumption to calculate our second state. So let's say we know that the entropy of the second state is equal to the entropy of the first state. We use that to find our enthalpy of the isentropic state, right? You guys remember doing that? Then we use the efficiency of our turbine to calculate our actual enthalpy, right? And you can do the same thing once you calculate that actual enthalpy, you can calculate the actual entropy as well. Okay? You're going to have to do that on your homework, so make sure you understand what I just said. So let's do an example that is an ideal Rankine cycle. So in this case, we're going to not worry about isentropic efficiencies, but I want you to think in your mind as we're going through this problem how you would do it differently if you needed to find the entropy at state 1, or the entropy at state 2, and the entropy at state 4. Okay, so this operates between the pressure limits of 2.5 megapascals and 100 kilopascals. So when I'm told that it's operating between these two pressure limits, what does that mean for this problem? How do I draw that on my diagram? Where do these pressures occur?
Coming out of the pump would be 2.5 megapascals.
Coming out of the pump, okay, 2.5
And going into the turbine.
megapascals, 2.5 megapascals.
100 kPa coming out of the turbine and then going into the
100 kilopascals is coming out of the turbine and also going into the pump. So the low pressure side is always the condenser and the high pressure side is always the boiler. If heat is supplied in the boiler at 800 Kelvin, so 800 Kelvin is our T sub H, and waste heat is expelled to the surroundings at 300 K, so T sub L is equal to 300 K, which is also going to be equal to the dead state because they just say it's expelled to the environment, to the surroundings. So we want to determine the exergy destruction associated with each process. So we already know from previously that the exergy destruction from what to what is going to be 0?
3 to 4.
Yeah, 3 to 4, and the Exergy destruction from 1 to 2 are both equal to 0. So you've solved half the problem right there. The Exergy destruction from state 2 to 3, what's the equation for that? So it's T naught times what?
S3 minus S2.
S3 minus S2
I don't know if it's plus or minus.
Q
okay,
Over TH.
minus Qn over TH. And why is it TH?
because it was the source.
Okay, because the heat is being transferred at that temperature. Piece of H. Okay, and then the Exergy destruction from what to what? We've got 2, 3. What's the next one
4
we
to
can
1.
solve? 4 to 1. How would we write that one?
S4 minus S1.
Yes, T naught times S4 minus S1
Plus.
plus
Yeah.
Q out over
TL.
sheath of L, which ends up being the same thing as T naught, right? Okay, so now in this problem we need to find the entropy at each state. So when we do that, we go look first at state 1. We're at 100 kilopascals. What else do we know about that state?
Wasn't that one S1 minus S4 in the other slide?
So it should be the outlet, yeah. Right. S1 minus S4. So it should be the outlet minus the inlet, S1 minus S4. Okay, so state 1, how do we find properties at state 1? We know it's at 100 kilopascals. What else do we know?
Saturated liquid.
Okay, it's a saturated liquid, so X is equal to 0. We can look up our entropy is equal to 1.3028, and our enthalpy is 417.51, and our specific volume is 0.001043 meters cubed per kilogram, kilojoules per kilogram, and S1 is in kilojoules per kilogram Kelvin. Okay, so we have state 1. What other state can we easily look up?
State 3.
Yeah, state 3, we have 2.5 megapascals at 400 degrees C. We would assume that it's going to be superheated, right, coming into a turbine. So we can look up the properties at state 3. We find S3 is equal to 7.0170, and H3 is equal to 3240.1 kilojoules per kilogram. And this is kilojoules per kilogram Kelvin on the entropy. Okay, so we know state 1, we know state 3. How do we find states 2 and 4? So far we know pressure.
S2 is equal to S1.
So S2 is equal to S1. S4 is equal to what?
S3.
S3. Okay, so we make the isentropic assumption. We can then go through and look up all the other property values. So state 2, we find that our our H2 is equal to V1 times P2 minus P1 plus H1. And so that ends up being 420.01. We have to use this because we don't have a pressure table for 2.5 megapascals. If it's a much higher pressure, like 10 megapascals, you can look in table A7 in the book. In your homework, I think it's higher. Okay, state 4, we know S4 is equal to S3, so then we end up having to calculate a quality of 0.944, and our H value is 2548.59.
What did you say again about using the pump work added to H1?
To find H2.
And
So, the work of the
don't
pump-
have to use it when it's a high enough pressure is what you're saying? It's for the tables.
So we have tables in our book, table A7, I think starts at like,
That's for the compressed liquids, right?
for a compressed liquid table, right? So it starts at 5 megapascals. So you could extrapolate off of the table and interpolate between lines and try to get it for 2.5 megapascals, or find some other source that has a table, or use these. Or you can make the compressed liquid approximation, which says that the work of the pump is equal to V1 times P2 minus P1, which is also equal to H2 minus H1. So then you can solve for H2.
So if you did that, and if it was above 5 megapascals, are those answers relatively close?
Yeah, they will be pretty close.
I think I did my homework.
Yeah, no, that's fine. As long as you did it correctly. So tables are always more accurate than making the
It's close,
approximation.
and I remember it was really close.
Yeah, it would be really close. And I've checked that on a couple of homeworks. I've done it both ways to see how close it is, just so I have both answers, because I know probably some people won't use table A7 because we never use table A7, hardly ever, because it's not very useful. So that's fine. Okay, where were we? So now we can calculate our Exergy destruction from state 2 to 3 is equal to 656.76. Oh wait. Okay, so Q in is equal to H3 minus H2. Q out is equal to H4 minus H1. So we calculate our Exergy destruction to be 656.76 and 3845.34. So then we can calculate our second law efficiency is equal to the work of the turbine out over the Exergy of the heat in plus the Exergy of the pump in. So that's H3 minus H4 divided by 1 minus T naught over TH times Q in plus the work of the pump, which is H2 minus H1, or V1 times P2 minus V1. So we calculate our second law efficiency, and we find that it's 39.3%. And I did that all on one slide. Okay, it was all crammed in there. But again, anytime we do examples in class, you can rewatch the video, and you can find PDF of it in the lecture notes online. Okay, so that's the second law analysis for the ideal cycle. Now that was kind of inserted into the middle of the chapter. Now we're going to talk about cogeneration, which is another way of combining processes or utilizing processes in a more clever way so that we waste less energy. So with cogeneration, in many cases there are manufacturing processes that their main production is heat for some process. Okay, so like their goal is to cook something or to refine something or to, do whatever with this heat. And so in many cases they're generating heat just using a boiler and a heater, or maybe electricity, or however they're doing it. They just need heat for their process, and so they're creating it. Well, if we implement, along with our process heater, some way of generating electricity, then we end up gaining more efficiency when we look at those two cycles disparately. So we could look at just a power plant that generates electricity, and we could look at a process heating plant that gives us heat. If we combine the two together, then we save more energy than if we're doing the two processes separately. So this process heat, or this idea of obtaining process heat as a byproduct of an energy production process is really quite useful to us. So any plant that produces electricity while also generating process heat is called a cogeneration plant. And it can be a gas turbine plant or a steam turbine plant, or it can be a combined plant, as just so long as it's generating electricity and it's also creating this process heat. So it allows us to produce electricity while producing heat. We can think of it that way. Or we could also think of it, it allows us to produce heat while generating electricity. So depending on what your end goal is, one of the two will be a happy byproduct. So either you're getting this extra process heat that you didn't have before, or you're generating electricity that you wouldn't have otherwise. And in some processes, they even use the process heat for something as simple as the HVAC system within the plant, right? So they have this waste heat. Instead of just expelling it to the outside, they can use it in the HVAC system in order to either run an air conditioner or use it directly as heat added into the plant to keep it warm in colder months. Now, there's something called a utilization factor, which allows us to figure out how much the energy that's being supplied to the plant is being converted to either process heat or electricity. And in the case where we have a plant that we somehow turn off the process heat, so really all we're doing is generating electricity, then this is equal to the thermal efficiency when there is no process heat. So you can see that at the net power output, if we get rid of the process heat, then it's just the same as the thermal efficiency. But when we're looking at in terms of generating electricity and or generating heat, we use the utilization factor because it accounts for both of those energy terms, because now heat is being useful for us. And in many cases, the loads will change throughout the course of the day or the week or the month or the temperature outside. It will change, your needs will change. So sometimes they don't need to create as much heat, or maybe they need to create more heat and so they turn off the turbine. In that case, they have a plant that's called an adjustable load plant, which allows you, using this expansion valve, to either divert all of your steam through the turbine or to divert all of the steam through the process heater. So depending on how far open that valve is, whether it's all the way open, all the way closed, then you may have some of your steam being diverted into the process heater. Sometimes you may not. So depending on what your end goal is, you'll do one versus the other, or a combination of the two. So when we look at the energy analysis for something like an adjustable cogeneration plant, this Q dot in is going to be the in that comes from the boiler, right? So this M dot 3 times H4 minus H3. And the Q dot out is going to be M dot 7 times H7 minus H1. So we're calling this Q out still, and this is Q in. But then we have a separate term for the process heater. So this Q dot P is going to be equal to M dot 5, so the mass flow rate coming through this expansion valve, plus whatever mass is bled off of the turbine, because we may do that at some point, minus this M dot 8 times H8. Okay, so to determine how much of your process heat is being generated, you need to look at it that way. And then the work of the turbine is going to be M dot 4 minus M dot 5, so minus whatever we're bleeding off to go to the process heater, multiplied by H4 minus H6, and M dot 7 times H6 minus H7. So let's look at an example of this. And this is a big wordy problem, but it's not that bad. So we have an ideal cogeneration plant shown at left with a boiler flow rate of 15 kilograms per second. So it's 15 kilograms per second is the mass flow rate here. If we look at this system, where else will the flow rate be 15 kilograms per second, regardless of what's going on with the valves?
11.
11, yes. 15 kilograms per second. Okay, so steam is entering the turbine at 7 megapascals and 500 degrees Celsius. So that's this temperature and pressure here. It's also going to be that same temperature and pressure here. So state 1, state 2, and state 3 are all at the same temperature and pressure. Some steam is extracted at 500 kilopascals, that's at state 5 for process heating, and the remaining steam leaves the turbine at 5 kilopascals and is condensed before being compressed again to the boiler pressure. So you can see all of these pressures are important to keep track of. So it's 5 kilopascals going into the condenser. It'll be 5 kilopascals saturated liquid coming out. It goes into the pump to be in the pressure to be increased to the same pressure as the boiler pressure. So when we throttle our steam here, it starts at 7 megapascals. We need to throttle it down to the same pressure that we're bleeding off of the turbine. So in this case, it's 500 kilopascals, which means also that in this process heater, which is essentially a mixing chamber as well, we're going to have 500 kilopascals coming out. And then our pump is increasing the pressure. What is it increasing the pressure to? State 10.
7 megapascals.
Yeah, it would have to be 7 megapascals because it will be combining with this fluid stream and then going straight into the boiler. So very important to look and understand all of the pressures and what's happening in the system, because you can't combine fluid streams of different pressures in a mixing chamber very easily. And when you're pumping something, you want to increase the pressure up to whatever it is that you're approaching. So if it's a mixing chamber or a boiler, you need to increase it to whatever pressure is necessary at that device. Okay, so at times of high demand, some steam leaving the boiler, oh, I already read that, okay. Assuming the extraction rates are such that the steam leaves the process heater as a saturated liquid, so X is equal to 0 at state 7, determine the maximum rate at which process heat can be supplied, the power produced when no process heat is supplied, and the rate of process heat supply when 10% of the steam is extracted at state 2 and 70% of the steam is extracted at state 5. Okay, so let's look at part A first. The maximum rate at which process heat can be supplied. When will that occur? Ugh. When will it be a maximum?
That's where will be applied?
Under what conditions will we have the maximum production of heat? So remember, this is a variable load system. We can divert it through the turbine, divert it through the process heater, some combination of the two. When will it be a max? Yeah, so when it's all the way open, your expansion valve is completely open, and everything is going here. Okay, so your turbine section is gone. That's part A. Part B, the power produced when no process heat is supplied. So B is sort of the opposite. This valve is closed, which means everything goes through the turbine. Okay, so two extreme scenarios. And then the third scenario, the rate of process heat supply when 10% of the steam is extracted at state 2. So this is 0.10 times m dot 1. And 70% of the steam is extracted at state 5. And it's a little bit unclear when it says 70% of the steam. So is it 70% of the steam that's going into the turbine? Or is it 70% of everything? In this case, we're just, for simplification, just going to say that this state 5 has 0.7 times m dot 1. Otherwise, we have too many flow rates we have to figure out. Yes?
So when, at state 2, like if you were to close the valve and it would just go all to the turbine?
Yeah.
Would the turbine work out be higher at that than it would if the valve would be open?
There would be no turbine workout. Wait, what are you saying?
We're,
When it's closed and everything's going through the turbine,
yeah.
that would be the max workout. Because you're not diverting some of that steam. So
So then-
anytime you're diverting steam from your turbine for some other process, you're reducing the available energy to be converted to work.
So then like, then you like shut the valve, all goes turbine, so then like states 2, 4, 5, 7, and 10 don't even matter?
Right. That's the extreme case, right? So if the valve's partway open, so some of it's going through, some of it's not, then you have to account for every state. But the two extremes in part A and part B are, one, that we only send it through the process heater, so all of this doesn't matter. Okay, it's like you just have this is your loop. That's part A. And then part B, it's like this is your loop.
So when the valve is all the way open, does it necessarily cut off the turbine part? Or
Yeah, there's gotta be another valve or something there. But this is an expansion valve that is also throttling the steam to different pressures, so it's analyzed because it changes the pressure. We can just assume that if this valve is open, then somehow it shuts off that. There should be, really, there should be another like switch or something. But
Would opening the expansion valve increase the pressure in the process heater or just provide a higher flow rate?
opening it, well, so it would have to be some kind of a variable expansion valve where you could, in reality, yes, it's going to change the pressure, but for this process, we're assuming it's a magical valve that only does one pressure. So there could be another way to restrict flow or divert flow that still allows you to have that same pressure drop, but yeah. It's a magical valve. It's a magical valve that when it's fully open, it also sucks everything through and doesn't allow anything to go to the turbine. So it's, again, a simplification. So sometimes reality doesn't match. But that's okay. All right, so let's go through and start figuring out states. So there's a lot of states on this thing, right? 11? Ooh, a lot. Okay. So let's go with the ones that are easiest, like state 1, which is equal to state 2, which is equal to state 3. So it's 7 megapascals and 500 Celsius. We have H1 equals H2 equals H3, which is 3411.4 kilojoules per kilogram. And then S equals 1, 2, and 3 is 6.800 kilojoules per kilogram. Okay, now state 4, because this is an isenthalpic expansion valve, H4 is going to be equal to H1, 2, and 3 as well. So this H4 is that same value, 3411.4 kilojoules per kilogram. So we found the first 4 states, that's pretty good. State 5, we know the pressure is 500 kilopascals, and we know that S5 is equal to S3, which is equal to S2, which is equal to S1. So S5 is 6.8, which means that we have to calculate an enthalpy of 0.996, and H5 we find is 2739.67. Can you read that? No? So we'll say, I'll write it down here, H5 is 2739.67. We do the same thing for state 6. S6 is also equal to S3, but in this case we can calculate H6 is 2072.96. These are both kilojoules per kilogram. And we found an X6 also is 0.799. Okay, state 7, we know that its pressure is 500 kilopascals and X is equal to 0, so H7 is equal to 640.09. So it's H sub F at 500 kilopascals. State 8 coming out of the condenser is at 5 kilopascals. And we can look that up because we also know that it's a saturated liquid. So H8 is 137.75 kilojoules per kilogram. H9 is equal to H8 plus V sub 8 times P9 minus P8. So we know P9, we know P8, we looked up H8 already, so we can find H9 pretty easily by calculating it. So it's 144.78 kilojoules per kilogram. And then H10 we find similarly by using the pump work and state 7. So it's H7 plus the work of the pump, 647.19 kilojoules per kilogram. So we found all of our enthalpies from states 1 through 4, it's all the same, and then 5 through 10. State 11, we don't actually ever need to use it, I don't think. That's 7 megapascals. It doesn't come up in this problem. Okay, so we've got those enthalpy values. Now let's start working on part A. So the max Q dot P occurs when all steam goes into process heater. So that means that the QP is going to be equal to the flow rate, all of the flow rate, times H4 minus H7. So we find that to be 41570 kilowatts. And part B, max W dot out, when Q dot P is equal to 0. So we find that's equal to M dot times H3 minus H6, which is the work of the turbine, minus H9 minus H8, which is the work of pump 1. Here, pump 1. So we subtract off the work of that pump. We don't have to worry about pump 2 because it doesn't come into play. So we find that's 19971.15 kilowatts. And then part C, we want to find Q dot P out when it's a 10-70 split. So it's equal to M dot 4 H4 plus M dot 5 H5 minus M dot 7 H7. And this is M dot 1 times 0.1 H4 because 10% of the mass is flowing through M4 plus 0.7 times H5 because 70% is flowing through H5 minus 0.8 times H7 because 70% or 80% is flowing through state 7. If the 10 plus the 70. Oh, that's messy. Here. Because you have this coming, here is 10% and here is 70%.
Oh, so those are additive, not multiplicative?
So that's funny, yes. Yeah. Okay, so then we find that it's equal to 26202 kilowatts at that state. In your homework, it's slightly different scenarios. So it'll say something like, the max, half of the max of the turbine work, what's your process heat going to be? Or for a process heat value of this, what is your turbine work going to be? So it's a similar process in analysis. You're going to have to figure out mass flow rates as you go through. So just enjoy it, and if you have questions, send me an email or come to office hours. Get started on your homework early and then you have time. Okay, so now we get to the grand finale of chapter 10, Or 11, for chapter 11. I was writing notes for chapter 11 earlier, so maybe that's why I'm confused. So, gas turbines operate at very high temperatures, and the exhaust is also very hot. So in theory, because they're operating at such high temperatures, if we were to have a very low temperature reservoir that they're rejecting heat to, they could potentially have high efficiencies. But they don't, because it's not possible to do that with gas turbines. So we have this really hot exhaust that's coming out, and we want to find a way to somehow use that in another process. So utilizing this hot exhaust gas as the heat for a vapor process is kind of a nice mix of both worlds. Because these steam vapor cycles often operate around 500, 600 Celsius at their high temperature. So combining them or stacking them together allows us to recoup some of those losses and to use that heat for another useful purpose. Rather than just rejecting it to the environment at a very high temperature, we could try to put another heat engine in between that heat and the environment in order to regain some of it. But we can't do another gas turbine because 500 Celsius is too low really to operate a gas turbine. We have to use another working fluid. So combining air with water, we can operate over a very wide temperature range from 1500 Kelvin all the way down, or 1500 Celsius, so it's like 1800 Kelvin, all the way down to 300 Kelvin. So it gives us a very large range. And these combined cycles have a higher efficiency combined than either of the two cycles separately. So again, this is another way of being smart about how we're using energy. Instead of just keeping everything distinct and operating, we can kind of make these hybrid systems that allow us to operate above the dome and below the dome and in many different places. So combined cycles look like this, where you have your combustion chamber for your gas turbine or your gas power cycle, which you combust these gases, they flow through the gas turbine, and as they come out, they're run through a heat exchanger. And usually it's a counterflow heat exchanger, meaning that it's coming in hot on this side for the gas and leaving at a cooler temperature on the other side, whereas the water's coming in cold on this side and coming out warmer to go into the steam turbine. And preferably it will be superheated at that point. So then we can exhaust these gases to the environment at a much lower temperature, which reduces environmental pollution as well as allows us to regain some of the losses from these exhaust gases by utilizing that heat that would otherwise be expelled. So then the steam runs through our steam turbine, similar cycle to what we've seen before. So this is a combination of a Brayton cycle and the Rankine cycle. And you can see that if we plot this on a TS diagram for water, where this is the dome for water, by using these gas properties, we're operating above the critical point, but it doesn't matter because the water temperature is not above the critical point. We're operating using the gas cycle above this critical point temperature and the steam cycle primarily under the dome. So again, it allows us to overcome the ineffectiveness of using water as a working fluid because it can't operate at such high temperatures because of the weirdness that happens up here. And also to recoup the losses from the Brayton cycle. So what's really nice about this is that you can see that the enclosed area for both of these cycles combined gives us a very large network output for the same heat input.
I have a crazy question. If 8 to 9 on the Brayton is the heat rejection, is the area under the line from 8 to 9 equivalent to the area under the Rankine cycle? Since that's the heat input into the Rankine cycle.
Like this area here?
Yeah, is that equivalent to the area under 2 to 3?
In an ideal cycle, it should be. It should be. This, I'm saying, this area here should be the same as this area here.
Yeah,
right?
that's what I was wondering.
Yeah, it should be, because Q in should equal Q out. What wouldn't be equivalent is from 8 to 5, because you're rejecting some heat still.
Right.
Yeah, but it should be the same value, because the Q should match whatever you absorb from, you know what I'm saying.
Yeah.
Q in from the gas is equal to, no, Q out of the gas is equal to Q into the water. Yeah, it should be the same. Okay, so if we look at the thermal efficiency of just the gas cycle itself, it's these enthalpy values, so H7 minus H8, which is the work of the turbine, minus H6 minus H5, which is the work of the compressor, divided by H7 minus H6. Then the vapor cycle, it's H3 minus H4, which is the work of the turbine, minus H2 minus H1, which is the work of the pump, divided by H3 minus H2. So that's the heat rejection in the, oh no, that's a Q in from the, what is now a heat exchanger. So if we combine the efficiency of those two cycles together, so we look at it as a total cycle rather than individually, you can see that this top number increases as compared to the gas turbine cycle. So we have H7 minus H8 plus H3 minus H4. We still have this minus H6 minus H5 and this, but now we've added this minus H2 minus H1. But this term is less than this other term that we added. So the combined efficiency is always going to be greater than the individual efficiency of these devices, which is a positive. Because again, the exergy of this heat in the combustion chamber, or the amount available to do work, is very high. But we have an inability to convert heat to work in a very effective way, particularly if we're only using one working fluid, because there's limitations to that, and we'll talk about that in a minute. So we have high exergy at a high temperature, and if we were to just quit right here, then we will have converted not very much of it to usable energy. But by changing working fluid, using that heat now in water instead of in the gas cycle, we can regain some of those losses. It's kind of exciting, I think, right? Just agree with me. It's better that way. Okay, so let's do a combined example. And in this case, we again have a lot of states to analyze, and we have to be careful because we have two different working fluids. So one of them is, we're assuming air at room temperature in this particular problem, so we're making like the standard, air standard assumption. And the other one is water. So what is different about analyzing air versus water? What equations can we use on air that we cannot use on water? Ideal gas. Okay, so you'll use the ideal gas equation here for this part of the cycle, but here you have to use tables. Okay, so by combining these two problems in one, just be very careful that you know what states are, what you've labeled, and that you're using the right method for determining property values. Okay, especially right here in the heat exchanger, because if you're looking at those as the same working fluid, then you'll have issues. Okay. But we know how to do this because this is nothing new to us. It's a combination of things we've already seen before. We should be able to analyze it fairly easily. Because we know the Brayton cycle, we know the Rankine cycle, and we know all of these individual steady flow devices, how to analyze them individually. So we can do it. Okay, so let's just get started. State one is the condenser outlet. It's 15 kilopascals. I guess we should put some of this stuff down. So air enters the compressor at 300 Kelvin. That's 300 at a rate of 14 kilograms per second. So the m dot of the air is 14 kilograms per second. And it's heated to 1500 K in the combustion chamber. So it comes out of combustion, 1500 K. The combustion gases leaving the gas turbine are used to heat the steam to 400 Celsius. So 400 degrees Celsius and 10 megapascals in a heat exchanger. The combustion gases then leave the heat exchanger at 420 Kelvin. So this temperature here is 420 Kelvin at state 9. Just be careful as you read the problem that you get the right temperatures. Yes?
Is that a typo? Because that means the steam is leaving the heat exchanger, or I'm sorry, the air is leaving the heat exchanger at a much colder temperature than, yeah, I think it's a Kelvin and Celsius. They put one when they meant the other. 420K would be like two.
Well, but it's a cross-flow heat exchanger. So the steam can't leave the heat exchanger at a higher temperature than the combustion gases are entering it. Right? So it's leaving.
Right. My question was, how is it heating the, because it's heating the water then to 673 Kelvin.
Yeah.
When the steam leaves it.
Because it's coming in at 1500. Well, it's not coming at 1500
You're right.
Kelvin, it's coming
Okay,
in at higher.
I'm sorry.
So if it were not a cross-flow heat exchanger, it couldn't do that. If it was a parallel flow, but cross-flow, it can do that, because it's coming in hotter here. Yeah. Good question, though. That's okay. Because, I do weird things all the time, so sometimes I make mistakes. Gotta get going. Okay. So the steam leaving the turbine is condensed at 15 kilopascals. That's the condenser pressure. So we know 10 megapascals, 15 kilopascals, that's the pressure ranges on this cycle. Assuming all the compression and expansion processes to be isentropic, determine the mass flow rate of the steam, the net power output, and the thermal efficiency of the combined cycle. And we can assume constant specific heats, which also simplifies our analysis. So let's go to the next slide so we have more room. And we'll just start knocking out the information on these states. So state 1 is coming into the pump at the outlet of the condenser. So it's 15 kilopascals, X is equal to 0. So we look up V1, H1, and S1 at 15 kilopascals, 0.001014. Meters cubed per kilogram. H1 is 225.94 kilojoules per kilogram. And S1 is 0.7549 kilojoules per kilogram Kelvin. State 2 is at 10 megapascals, and here's one where you get to use table A7. That's 7, sorry. A7. So we have 10 megapascals, S2 is equal to S1. We can look up our H2 value is 236.58 by interpolation. State 3, we have 10 megapascals, 400 degrees Celsius. So we can look up H3 is 3097.5 kilojoules per kilogram. And S3 is 6.2141 kilojoules per kilogram Kelvin. And then state 4, which is the end of our liquid properties, we find P4 is 15 kilopascals, S4 is equal to S3. We go to the tables, we have to calculate quality as 0.75, and H4 is 2011.77 kilojoules per kilogram. Okay, so we've looked up all of the properties in the Rankine cycle. We now need to find properties in the Brayton cycle, and because it's an ideal gas, we can't use the table. Well, we could use the tables to look them up, but we're given the permission to assume constant specific heat, so we're going to use it that way. So we can say that T7 over T8 is equal to P7 over P8 to the K minus 1 over K. So that allows us to find T8 is equal to 679.3 Kelvin. And this P7 over P8 is given to us in the problem as 16. So similarly, we can do T6 over T5 is equal to P6 over P5 to the K minus 1 over K. And we find T6 is equal to 662.45 Kelvin. Okay, so we were given already T7 and T5 in the problem. T7 is equal to 1500 Kelvin and T5 is equal to 300 Kelvin. Okay, now it's just a matter of solving our problems. So part A, we're trying to find the mass flow rate of the water. So we know from the heat exchanger that the mass flow rate of the gas multiplied by C sub P T8 minus T9 is equal to the mass flow rate of the steam multiplied by H3 minus H2. So then we find the mass flow rate of the steam by rearranging using 1.005 kilojoules per kilogram Kelvin for C sub P is 1.275 kilograms per second. Part B, we find the work of the gas turbine is equal to m dot G C sub P times T7 minus T8. We plug in the numbers for that, and it's 11547.25 kilowatts. The work of the steam turbine is equal to m dot of the steam times H3 minus H4. So that's 1384.31 kilowatts. The work of the compressor, actually these are all powers, is equal to m dot G C sub P times T6 minus T5. We find that to be 662.45. No, that's the temperature. Sorry. 5099.67 kilowatts. And then the work of the pump is equal to m dot of the steam times H2 minus H1, which is equal to 13.56 kilowatts. So work.net is going to be equal to the work of the turbines minus the work of the compressor minus the work of the pump, 7818.33 kilowatts. And the thermal efficiency is equal to the work net over Q in, where Q in is equal to m dot of the gas turbine C sub P times T7 minus T6. So that's the Q in to the combustion chamber, from the combustion chamber. So we find that to be equal to 66.3%. Wowee, I haven't seen efficiencies that high since we were dealing with the Carnot cycle. Okay, so again, it's just plugging through, finding all the property values, making sure that you know and understand how to calculate work terms and heat terms and using the correct enthalpies. So one last note on that, rather than combining a vapor cycle with a gas cycle, it's also possible to combine two vapor cycles of differing working fluids together in order to achieve similar results. Because water is a good working fluid, it's readily available, it's cheap, it's easy to operate, but it's not ideal because of the critical point being so low that we can't operate above the critical point without weird things happening. So if we separate the process into a high temperature working fluid and a lower temperature working fluid, then we can operate all over the dome, similar to what we did with the gas vapor power cycle, and it allows us to increase the overall efficiency. So some ideal characteristics of working fluid are listed here. You want a high critical temperature and a safe maximum pressure, a low triple point temperature, so that's the temperature at which solid, liquid, and vapor exist all together. So similar to the critical point, you don't want to operate near it if weird stuff happens. Your condensation pressure should be near atmospheric. You don't want them to be too low because then in your condenser, if you're sub-atmospheric pressure, you can have leaks and problems and it's hard to maintain that pressure. A high enthalpy of vaporization, so that means that when you're operating under the dome is the distance across the dome, or how much energy you can remove in the condenser. And then you want the saturation dome actually to look like an inverted U. So what that means is when you have this inverted U, if you're operating in like the Rankine cycle and you're coming down here from your turbine to the condenser, if this line is very far out, then you'll hit this saturated vapor line sooner, which means you'll have more moisture in your condenser. So the steeper this line is, the saturated vapor and the saturated vapor and saturated liquid lines, the steeper those are, the better it is for these processes, because you can almost even use a Carnot cycle. High thermal conductivity, and then of course cheap and easily available. So this is one example of a binary cycle that uses mercury in water. Mercury, again, is kind of a dangerous working fluid to have because of its toxic nature, but mercury does allow us to operate at higher temperatures and still get some pretty neat results because of its low, or its high critical point itself, that it has a much, much higher critical point than water. So we're not doing any problems with these, but it's interesting to think about and know that that exists and is in operation. Actually, I think there's a mercury water power plant in the UK. So, very interesting. That's it for today. See what the emergency is.